I'm going to introduce you to Dr. Janos Kirz. It's a real pleasure and an honor to meet. Dr. Janos Kirz was born in Budapest, Hungary. He got his PhD from the University of Berkeley and 2 years, and then he did his he was working in labs in Alvarez's group under the direction of Bob Tripp. After that, he spent a year as a postdoc in CEN in France, returning to Berkeley lab the following year. In 1968, Kirz joined the faculty of Stony Brook University, where he continued to work in high-energy physics until the 1980s, performing experiments at Brookhaven National Laboratory, the Stanford Linear Accelerator Center, and Fermilab. He became interested in X-ray optics and in synchrotron radiation during a year spent in Dorothy Hodgkin's labs at Oxford University, and subsequently devoted his time to the development of X-ray microscopy, spectral microscopy, holography, and diffraction imaging at the National Synchrotron Light Source. He then spent a part of a sabbatical year at Berkeley Lab during 1993-94, and a full year in 2002 and 2003, during which time he initiated an experimental program of the ALS in diffraction imaging. He served on the LAS Users Executive Committee for 1987-89 period, on the Scientific Advisory Committee, and several review committees. Right now, he is enrolled in the Lawrence Berkeley National Laboratory. He's working there, and he's doing several advisory and management. And he is no longer enrolled in Stony Brook, not directly enrolled in Stony Brook. That's a mistake we did in the poster. And well, he has received several. He's a member of several associations, and like the member of Advanced Light Source Scientific Committee. Has been chair of the search committee for director of Brookhaven National Laboratory, and recently the NAL Nano Center Program Advisory Committee from 2003. And his interests rely on synchrotron radiation, microscopy, X-ray science, and technology. So please welcome Dr. Janos Kirz.
Thank you very much, Francisco. I must say I'm delighted to be here. It's a beautiful town, a beautiful university, and I've never been here before, but I'm thrilled to be here. As Francisco told you, I've been playing with X-rays now for over 30 years, and I'm going to take you on an adventure having to do with X-ray optics. But I want to, in particular, dedicate this lecture to the memory of Albert Baez. Albert was born in Puebla, Mexico. I met him about 20 years ago. It would be just a couple of days from the anniversary of his death in 2007. He is truly one of the pioneers of X-ray optics, as I hope to persuade you. But he is better known to the popular world as the father of Joan Baez, the famous folk singer since around 1970s, 80s, 90s, and she is still active today, and also Mimi Farinha, who died earlier on. But we have to go back to before the time that Albert Baez was born, to the year 1895, which was truly the start of a truly remarkable period. It is hard for us to imagine today, 1895, There was no email, no PCs, no Skype. There were no telephones. There were no airplanes flying passengers all over the world. It was a different time, but physicists were very excited about studying discharge phenomena. They had these evacuated glass tubes with electrodes going through them, and they were sort of like neon lights today, but they were operated by high voltage supplies, and people were looking at the light due to the discharge near the anode of this discharge tube. And in fact, people knew actually for the previous couple of years that what caused this discharge and the light were electrons, and they were even able to extract the electrons through thin windows in this glass tube. And they were studying them in every laboratory all over the world. However, it took Mr. Röntgen, who was a very careful experimenter and not a particularly well-known guy, and he was not one of these hotshot young people. He was 50 years old. But he had a laboratory where he was looking at these discharge tubes. And he covered his discharge tube in black paper. He was looking at the effects of the electrons emerging from his thin window. And he did that for some reason in a darkened room. I don't know why he darkened his room, but the fact is that he did. And quite by accident, on a table some meters away from his discharge tube, he had a screen of fluorescent paper. And he noticed that when he turned the high voltage on his discharge tube, that fluorescent paper lit up. He didn't know why. No one has ever seen an effect from a discharge tube several meters away. Now, the thing which makes a good scientist into a great scientist is to recognize that this is something which is really a very interesting thing that really deserves careful attention. And he devoted 5 weeks, almost day and night, in his laboratory to try to understand what was going on. And he pretty quickly recognized that he could detect these rays on a photographic paper, and that if he put material between the discharge tube and the photographic paper, this would leave shadow graphs on the photographic paper. Furthermore, he discovered that if he put his hand in the way, he would see the bones of his hands. Now, what I'm telling you, you all know, but he discovered all that within that 5 weeks of effort. Furthermore, he made careful measurements to see that this radiation travels in a straight line, and there was no way to deflect it, or to bend it, or to focus it. And he did a great many careful experiments. The first observation was in November 1895, and right around Christmas time, he wrote up his 12-page report on it. And you know, if you write a paper these days, you submit it for publication. Sometimes it takes 6 months to get the thing out. Sometimes it takes a year to get the paper published. In 3 days, he got the printed copies from his publisher, which was the local medical group. He mailed it, and as I mentioned, there was no fax those days. He put it in the mail to his colleagues in Vienna, in Berlin, and in other parts in the neighborhood, along with some pictures that he recorded on photographic paper. On the 5th of January, one of his colleagues received the paper. On the 6th of January, the discovery was featured on the front page of the newspaper. On the 23rd of January, he was invited to the Emperor of Prussia, where he received a medal, and on his way back to his town of Würzburg, he had a ticker tape parade from the students. By the end of January, his experiments were repeated in 24 places around the world. And within a couple of months, people were using X-rays to find bullets in people's bodies. And in April, there was a warship traveling up the Nile, where there was a medical emergency room with an X-ray machine to treat the wounded. So if you think that today things move fast, boy, things moved fast in 1896. The number of papers published on X-rays in 1896 was over 1,000. This discovery just spread like wildfire, and as I have already told you, the first paper, which is a masterpiece of how you should write a paper, already includes the measurement that if there is an index of refraction for materials in X-rays, it is less than 1.05. To remind you, it's about 1.5 for glass and 1.3 for water, but it is closer to 1 for X-rays. And, well, in 1896, Alfred Nobel was still alive, so there were no Nobel Prizes. But when the first Nobel Prize was awarded in 1901, Mr. Röntgen got it. Now, as of that great discovery, we all knew that X-rays traveled in a straight line, so to build optical instruments involving X-rays seemed not particularly hopeful. So for people who were interested in not just creating contact images, contact prints, photographs, but wanted magnification in the pictures in order to do anything like microscopy, what people started to do is to do projection imaging, where what they tried to do is to make the X-ray source as tiny as possible, as point-like as you can get, which means that what you want to do is to focus the electrons that generate the X-rays to as small a point as possible, and then you put your object that you want to image into the diverging rays of X-rays, and if you put your detector at some distance, you get magnification. And this was a cottage industry that was perfected particularly by Vernon Coslet and Theodore Hall in the 1940s. And you can even today buy projection microscopes, but what I wanted to point out in particular, just as a matter of interest, that in the 1990s, after Coslet died, people discovered equipment in his attic which made it clear that aside from working on electron X-ray microscopy, his main activity was to spy for the Soviet Union. And Theodore Hull, who before 1946 happened to be in Los Alamos National Laboratory working on the atomic bomb project, escaped to England in order to avoid being caught as a spy for the Soviet Union. So that is not really relevant to X-ray optics, but I want to get back to the index of refraction. And as I mentioned to you, for visible light in transparent media, typically you have an index of refraction of 1.5 or something like that. And if you want to build lenses, lenses work by refraction. And for simple lenses, the inverse of the focal length depends on the inverse of the radii of curvature of the lens. But in particular, there is this factor n-1 in front of it, which is a critical number. Now, if n is 1.5, then n-1 is a half. And so the focal length will be of the same order in magnitude as the radii of curvature. So if you make the radii of curvature a centimeter or two, you are going to have focal lengths which are a centimeter or two. And everything works out fine as you expect. Now, if you are interested in mirrors, then typically you don't start with transparent media because they don't reflect terribly well. You coat with some metal layer, and you end up with a complex index of refraction. But nevertheless, you get good mirrors, and that also helps you use focusing. But the question is, what is the situation with X-rays, where we have already seen that the index of refraction is going to be much closer to 1. And in fact, it has not been measured until for some decades after Röntgen's original work, until a fellow by the name of Albert Einstein wrote a little paper where he came to the stunning conclusion that the index of refraction is not only close to 1, it is slightly less than 1. Now, this was the first time that anyone encountered a situation of an index of refraction being less than 1, and this is the sum total of Einstein's paper. And I imagine not too many of you can read such tiny script or understand German, but here in similarly tiny script, it is in English, where it says that the difficulty in determining n, the index of refraction, lies in the fact that n-1 is very small. It says here about 10 to the minus 3, it's a typo, it should have been 10 to the minus 6. But it is obvious that for almost grazing incidence, there must be detectable total reflection for X-rays in the case where n is less than 1. So let's examine the story. For a lens, as I indicated, if you have n-1 on the order of 10 to the minus 5 or 10 to the minus 6, you will find it hard to make the focal length because this is the inverse of the focal length that is proportional to 10 to the minus 5. The focal length will be on the order of 10 to the 5 times the radii of curvature. So the focal length is going to be hundreds of meters. That's not a very good lens for most of us who are interested in doing focusing. However, and I will come back to lenses later on, but I will come back to what Einstein was saying about critical angles. And so let me remind you about refraction. Under normal circumstances, if you have an optically denser medium like water, and you have a surface with air, you have ray incident on the interface, it will be refracted. And if you increase the incident angle, at a certain point, the refracted ray comes grazing parallel to the surface, And if you increase the angle even further, this ray doesn't get out into the medium, but gets totally reflected. This is what we call total internal reflection, and it is your usual experience that we use every day. But here we assume that the index of refraction for a medium is greater than 1. If the index of refraction for a medium is less than 1, then it turns out that it is the air that becomes the optically denser medium, and the critical angle is when you are incident at a grazing angle from air, and you are going to have total external reflection from material, and this is what Einstein was talking about. And it turns out that if you calculate what is the connection between the critical angle and the index of refraction, you are in luck. Because the critical angle is proportional not to the difference of n minus 1, but the square root of the difference n minus 1. So when n minus 1 is on the order of 10 to the minus 5, the square root of that is 3 times 10 to the minus 2. So the critical angle will be on the order of a fraction of a degree. You can even make it a couple of degrees if you use the right materials, so you can actually get reflection from a surface. So if you can get grazing incident reflection, that's good, but, and this is another slight divergence, keep in mind you have to be careful. What you learn is that if you are a material medium, the velocity with which electromagnetic waves propagate is the velocity of light divided by the index of refraction, n. Now, if n is less than 1, this simple equation tells you that you are going to propagate at a velocity greater than the velocity of light. Now, most of you know, and if you read the newspapers in the last year, you probably have discovered that people get very excited if somebody comes up with the idea that anything goes faster than the velocity of light. But if you have had a course in optics, you know that there is a difference between what we call phase velocity and group velocity, and this simple equation tells you only about the phase velocity, the rate at which the peaks of the wave move. But the rate at which information moves, if the index of refraction depends on the wavelength, is the group velocity, and that is okay. So you don't need to lose any sleep. In fact, it was Mr. Einstein himself who suggested that for X-rays, the index will be less than 1, and he didn't lose any sleep over it because he understood that it does not contradict his theory of relativity. So coming back to grazing incidence mirrors, what I want to tell you that it is really quite remarkable how you can build capillary condensers out of glass or coated glass, silicon, or metal, which work well for hard X-rays, and you can build capillary condensers which can take a beam of X-rays shown here in yellow and focus it down on some sort of a sample that you might be interested in. And one of the most remarkable things with tapered capillaries was done by Don Bilderbach and collaborators. And they were able to look here, the scale is a ½ micron, and they were able to take objects and image them with a resolution on the order of ½ micron by focusing with tapered capillaries. Today, actually, people make better tapered capillaries. I think my friends at the company X-Radia make some of the best tapered capillaries. And one of the nice things about these is that they don't care what the wavelength is. They work the same for all wavelengths. But if you want to do some real optics, you may want to have some carefully figured surfaces. And you know about ellipsoids. Ellipsoids are really very nice because they have the property that they have pairs of foci. And light that emanates from one focus is collected all to the other focus, no matter where they bounce. Now, this doesn't show you grazing incidence, but you can make ellipsoids which, instead of being sort of like a football, are very long and cigar-shaped, and there is a region there that you can arrange to have grazing incidence. But the problem that you are going to encounter is that depending on where you bounce, the object distance from the mirror and the image distance to the image from the mirror is going to vary, and therefore you are dealing with variable magnification. And what that means is that if you have more than a point here, an extended object, different parts of the object will be magnified a different amount, and therefore an ellipsoid is not an image-forming element. Nevertheless, there was a group at Hamburg in the 1990s which, under the direction of Christoph Kunz, that tried to use a piece of an ellipsoid in order to form a demagnified image of an X-ray source and create a microscope by scanning this sample with this source. But it turned out not to be very successful, and it had to be abandoned. However, the idea of using grazing and incidence with X-rays continues on, and the person who was particularly active in this area is a fellow by the name of Kumakov from Moscow, and he invented the polycapillary lens, which is made up of bundles of hollow fibers. In each of the fibers, which are bent to, so this is a little bit exaggerated here to what extent it is bent, but basically you do a bunch of grazing incidence reflections and you can guide X-rays around the curve, and so you can easily see that if you have an X-ray source here, this bundle is going to orient most of the X-rays to this object. So if you want to make an efficient use of an X-ray source, a conventional X-ray machine, and direct more of the X-rays onto some sort of a target over here, a polycapillary array is actually a pretty good gadget. And nowadays you can buy that from a variety of companies, and all that is depending on multiple grazing incidence reflections. But the real breakthrough came in this paper by Paul Kirkpatrick and Albert Baez in 1948 in the Journal of the Optical Society of America. This paper has been cited in the literature by 570 times as of the time when I prepared this lecture, and probably more since then. It is one of the really famous papers, and on my flight over here, I reread it. It is a fabulous paper, and I would strongly urge you to become familiar with it. Basically, what the paper says is that if you use a spherical mirror at grazing incidence, and you have a point focus of X-rays, and you put a little spherical mirror here, and the X-rays are incident, then a point here will, if it reflects on one point, will go in a particular direction. But if the ray goes off toward you, it will keep on going toward you, it will get deflected. But if the ray comes this way, it will come this way again. And so the point will not be focused to a point, it will be focused to a line. But if you observe the rules of reflection from mirrors, that line will be sharp at a certain distance from this spherical mirror. Okay? So you have a good way of taking a point and focusing it into a line. That is exactly what a cylindrical mirror or a cylindrical lens would do for you. It is a perfect focusing element in one dimension. Now, when you want to take a picture, you typically don't use a cylindrical lens. You use a spherical lens. You want to focus in 2 dimensions. But in particular, what Kirkpatrick and Baez pointed out was that if you combine 2 of these at right angles, you can get point-to-point focusing. And so the breakthrough is that if you have a bundle of incident hard X-rays, you bounce once from a spherical mirror here, bounce from another one which is oriented at right angles, and you get a point focus, and this is an image-forming element. And in fact, Kirkpatrick was so excited about this discovery. Kirkpatrick was Baez's thesis advisor. They did the appropriate calculations of the performance of the optics. They discovered that this arrangement canceled astigmatism. And Kirkpatrick wrote an article in the Scientific American of 1949. That was the year after this paper appeared. And the title was The X-ray Microscope. And it said, on the table of contents, it said, it would be a big improvement on microscopes using light or electrons for X-rays combine short wavelengths, giving fine resolution and penetration. The main problems standing in the way had now been solved. Well, unfortunately, it took another 30 years before X-ray microscopes started to actually solve problems. It was a little bit difficult to make these, but the article in the Scientific American showed the major discovery of the Kirkpatrick-Baez lens. And today, these Kirkpatrick-Baez lenses are used widely to form microprobes, both in conventional X-ray laboratories and at synchrotron light sources. They are used widely to relay any source to a target, and people continue to refine them in a variety of ways. And this is just sort of the first installment of where Baez has made his mark in X-ray optics. But the next item that I want to mention came a decade later when Baez was working for the Smithsonian Astrophysical Observatory at Harvard. By that time, Sputnik has been up, and people, the space race has started, and people started thinking about doing X-ray astronomy. Now you understand that in astronomy, you typically, unless you are looking at the sun, you are dealing with very little light. So in astronomical telescopes, people try to make them as big as they can. And a Kirkpatrick-Baez mirror intercepts very little light. So in order to make it sensible to build an orbiting X-ray telescope, it was necessary to find a way to increase the amount of light that the telescope could intercept. And so Baez, in this paper, came up with the idea of doing stacks of these Kirkpatrick-Baez mirrors. And in fact, this is the idea that is the basis of all X-ray telescopes that have been built ever since. Now, they may not use the same optics as I will explain, but they use the same idea of the stacks of mirrors. And to come one step further in terms of not the same optics, the paper by Kirkpatrick and Baez mentions the fact that the spheres are the ones that everybody can make. I think you are aware of the fact that the reason why people love spherical mirrors and spherical lenses is because if you take any two surfaces and rub them against each other, if you keep rubbing long enough, they are going to be spherical. Okay? Any other surface is very hard to make. But in 1952, this was 4 years after the paper by Kirkpatrick Baez, Hans Wolter in Germany did the very nasty, complex algebra. And there is nothing more to it than algebra and trigonometry, but it's pages and pages and pages of equations to remove the third-order aberrations in order to make a completely aberration-free optical system. And he found that there are 3 types of systems that he can build, making a combination of 2 mirrors, okay? These are either you take an X-ray beam and you reflect it first from a hyperboloid, and then first from a paraboloid, and then from a hyperboloid, and then you get an aberration-free image. Or you can reflect first from a paraboloid and then from a hyperboloid, and that gives you a longer focal length, and so on. So there are ways of doing that, but to make these mirrors and to align these mirrors is very difficult. And it has not been until about 10 or 15 years ago that people have actually succeeded in developing the technology of making these. But these are not the kinds of things that you go down to the store for and buy for $10. These are the ones that are the multi-million-dollar mirrors that are in today's X-ray telescopes orbiting the Earth. So we have talked about how we can make use of grazing incidence reflection. After some decades of struggling with the fact that grazing incidence is not very convenient, people have started to ask, is there any way that we can enhance the reflectivity and go from grazing incidence to normal incidence, the way we like to use mirrors? And the person who I think is really responsible to come to a fruitful scheme of doing things is Eberhard Spiller. Now, the reflectivity of a surface at normal incidence is given by this simple expression. And you remember for X-rays n-1 is on the order of 10 to the minus 5. N plus 1 is 2. So if you take 10 to the minus 5 over 2 and you square it, you get a very small number. So the reflectivity of X-rays at normal incidence, forget it, right? Is there any way to get around that? And what you want to remember is that if you reflect at normal incidence, what happens is that there is a wave coming in, that's the black one, and it bounces off the surface and goes back. And whether you have a node or an antinode at the surface depends on the nature of the surface. That's not of importance to us now. But what is important is that you set up standing waves which have the characteristics that if this is a wavelength, every half wavelength you have a node. You have 0 amplitude in the wave. Okay? So what happens if you put another surface right here and another surface right here, and another surface right here, and another surface right here, you can teach the wave that it should have nodes at those places. And if you can somehow arrange to have hundreds of these surfaces at the nodes, you can add the reflectivity of each of these surfaces. Now you might think that if your reflectivity is 10 to the minus 10, you will need 10 to the 10 surfaces. No. You're lucky, once again, because it is not the reflectivity or the intensity that adds, it's the amplitudes that add. So all you need is 10 to the 5 surfaces, not 10 to the 10 surfaces. Now you say, even 10 to the 5 surfaces is an outrageous number. But this index of refraction, which I told you is 10 to the minus 5, is highly dependent on the wavelengths. And if you go from a wavelength of an angstrom to a wavelength of 50 angstroms, which is in the soft X-ray regime going toward the ultraviolet, the index of refraction is 10 to the minus 3, or the n minus 1 is about 10 to the minus 3, and 1,000 surfaces will suffice. Now you will say 1,000 surfaces is still a lot. Except that in today's technology, it's not outrageous. People are building multi-layer coatings with 1,000 layers. And the only thing you have to worry about is that material absorbs X-rays as well. So what people do, they select very carefully the materials that they use. They use an X-ray transparent layer to space the absorbing layers so as not to lose too many X-rays. And as a result, if you have those hundreds, maybe 1,000 layers in a multi-layer, you can generate reflectivities of, people have demonstrated 68% reflectivity for X-rays with a wavelength of 112 nanometers. Why do I mention 112 nanometers? Because it is industrially very important. So let me try to explain. What happens is that, as I mentioned, amplitudes add, you need hundreds of layers, and you have to space them at half the wavelengths if you want normal incidence. And where you use them is with a Schwarzschild objective. A Schwarzschild objective consists of two spherical mirrors. One mirror surface is here, one mirror surface is here. These are concentric, so the center of the circles is over here. You have light coming in, bouncing off this small spherical mirror, so as to reach the second mirror at large angles, and then with a good large numerical aperture, you focus the light onto your sample. This is an arrangement that has been known for 100 years or more. You can buy a Schwarzschild objective for your regular visible light microscope from any number of optical companies. People like this arrangement because the distance between the focal point and this mirror surface is larger than with a regular lens objective. So if you need space around your object, then the Schwarzschild objective is a very nice microscope mirror. Now, what Spiller and company and his collaborators did was to put those 1,000 layers of reflection-enhancing coating on these surfaces, and now they can form this very good image with 112 nanometer wavelengths. You cannot form images with lenses or any other ordinary mirrors at that short a wavelength. Why is this relevant? Why are people excited about it? The reason why people are excited about this is Moore's law. You all know about Moore's law. You all benefit about Moore's law. Your computers become faster because there are more transistors on a chip, and it doubles every year and a half. But people have been going from doing the fabrication by projection printing these circuits, first with visible light, then with ultraviolet light, then with deep ultraviolet light. They had to get away from using glass lenses to calcium fluoride objectives and other crazy exotic materials in order to deal with the shorter and shorter wavelengths that you need to get this finer and finer circuit elements. Okay, so they have run out of the way to make these. The wavelengths has to be even shorter to make the lines even finer. So they are now down to the extreme ultraviolet, where no lenses or mirrors work, except this multi-layer coating objective. So people have been working and developing this technology, and because it needs multiple mirrors to demagnify your circuit diagram onto the tiny chip, you need very good reflectivity, and that's where these multi-layer coatings are clearly paying off in a big way. So I want to now change tone and talk about an alternative to mirrors. And here I'm getting to diffractive optical elements. You can deflect waves by diffraction gratings. And this has been known for a long time, and the angle by which you deflect is the wavelengths divided by the spacing of the grating with the order number in front. And, but it has not been used to focus until in the 1870s. Lord Rayleigh discovered that if he makes a circular diffraction grating with a radially increasing line density, and this is a plate from R.W. Wood's 1898 article, then this works as a lens. And it is really incredible. Basically what you have to do is, if you look at this in cross-section over here, you make the open rings so that the distance of the line to the focus increases by the wavelengths as you go from opening to opening. And because it's a diffraction grating and has multiple orders, you are interested in the first diffraction order because that's where most of the light goes. And you can easily see that the deflection angle will be the wavelengths divided by the period at the outer edge. And the Rayleigh resolution with that sort of numerical aperture or maximum angle will just be 1.22 times the finest line you can fabricate. So if you want very fine lines, you probably don't want to give it to the machinist in your machine shop. You have to somehow use some very high precision fabrication technology, and you need to position this with very high accuracy. And so what I want to emphasize that it works just like a lens, except if you use opaque zones, only 10% goes into the first order focus. If you shift in the zones, you can get up to 40%. If you blaze the zones, you can get even more, except for the absorption in real materials. It is a chromatic objective, but it has no spherical aberrations. And you can easily, if you have a plane wave incident, you can isolate the first order focus by just having an aperture between the zone plate lens and the first order focus, and that's the way we use it. And here I return to my hero, Albert Baez. He was the one who pointed out in 1952 that zone plates, which were of course used for visible light and was not quite what it is today, but this is the zone plate which is made up of gold rings held together by these struts, but the open zones were entirely open, and he demonstrated that he can use to focus ultraviolet. Now today there are more modern techniques. Günther Schmal and collaborators in the 1970s used holography to make the zone plates, and my friend and colleague David Sayer pointed out that with the technology that is built for microfabrication of circuits and so on, you can use these electron beam fabrication techniques to make zone plates of exquisite precision. This is now 10 years old. It says new, but it was new 10 years ago. And you notice these concentric circles, this cylindrically symmetric diffraction grating. The outer lines and spaces are 25 nanometers in size. This creates foci which are 30 nanometers across. By 2005, they went from 25 nanometers to 15 nanometers. And here the finest focus that you can generate is about 18, 19 nanometers. And that is the finest focus, far-field focus you can generate of electromagnetic radiation of any wavelengths. Because if you go to longer wavelengths, well, diffraction spoils it. If you go to shorter wavelengths, the technology doesn't allow you to do it. So this is really a sweet spot in terms of being able to focus things. And these are used for microscope objectives, for microscope condensers, and because they are so chromatic, they can be used as monochromators. They can be used to form microprobes, and because there are multiple orders, they can also be used for beam splitters, and they work for any wave. In fact, Baez's 1961 paper mentions already, if you want to focus neutrons, these will work just as well, and that has also been demonstrated. The challenges are how to get to even higher resolution, even higher energy, and higher efficiency, and that requires high aspect ratios. And just to illustrate you what I mean is, look at these zones. They are something like 50 times as thick as wide, because you have to keep the spacing very tiny. That determines the resolution, but you still want to affect the radiation, and that requires the same thickness as you have at larger spacing. And this is a real challenge to fabricate, and people have learned how to do this in very high-tech laboratories at Bell Labs and IBM and at microfabrication technologies. But I want to also get back to the one other topic before I let you go, and that is the question, are real lenses really hopeless? And you remember we talked about the index of refraction, and that it differs from 1 only by a slight, very small number, and because of absorption there is also an imaginary part. And therefore, because this is a negative number, your lens, instead of being a piece of glass in air, will be a piece of air in glass. Okay? So it is really a hole that is a converging lens. And the single hole, we decided, will have a focal length of 100 meters, which is not particularly good. But it was pointed out by Bing-Sin Yang, who had been my graduate student some years earlier, is that if you could somehow form a string of bubbles, the combined effect will shrink the focal length. And you know, it's very hard to fabricate a string of bubbles and hold them all in an accurate straight line. But then a couple of ingenious people, Anatoly Snigerev and Bruno Langler and company, published this paper in Nature in 1996, pointing out that you can do it. But you can use the same trick as Kirkpatrick and Baez did, go in one dimension at a time. Instead of using bubbles, you drill holes. And an accurate milling machine can drill a nice line, a series of holes, one after the other, and that will be a nice cylindrical lens. And if you take two of these at right angles, you can make a point-to-point focusing lens. Unfortunately, if you just do that, you get pretty bad spherical aberrations. But if you can make your holes paraboloidal instead of cylindrical, that fixes the spherical aberration. And so what people have learned to do is to make paraboloidal holes, they put them together, and they now have very nice image-forming elements. They don't have the same resolution as zone plates, but they do have the nice characteristics that they can be microfabricated and they don't worry about too much power. If you have a very powerful laser, they don't get blown away as a zone plate would be. And the alignment is much easier than for Kirkpatrick-Baez lenses. Unfortunately, they are chromatic. So, to summarize, basically, depending on what the wavelengths you are interested in, at the longer wavelengths, you use the Schwarzschild Objective with a multilayer coating. For soft X-rays, you use zone plates. For harder X-rays, you use either zone plates or Kirkpatrick-Baez lenses. For hard X-rays, you use either Kirkpatrick-Baez lenses or these refractive lens arrays. And the best focus today is on the order of 10 nanometers. These are used in X-ray microscopes, and I'll talk about that tomorrow, in X-ray telescopes, in X-ray therapy, in crystallography, and in many other areas. And I just want to end by thanking the local chapter of the Optical Society and the current president, the past president, and the advisor, and the Optical Society itself that paid for my airplane. Thank you very much.
Okay, so if anyone has any questions for Dr. Janos?
Yes.
So for fabrication now of chips, the size is now 30 nanometers or so. Is the technology then does not zone plates, or what are they using nowadays?
They use an incredibly complex phase-shifting mask with krypton fluoride lasers and calcium fluoride optics, and they are still not using this EUV lithography. This is for future generations. They are planning on future generations, but they are not there yet.
But it's also a phase contrast imaging.
It's phase contrast imaging, and one of these plants that does the manufacturing, it's incredible. They build a new plant every year and a half for the new technology, and each of these plants costs multiple billions of dollars. And that's why there are maybe 3 or 4 companies in the world that can keep up with this investment.
Are there any other questions? you can ask in Spanish, pueden hablar en español y intentamos traducir. Okay, I have a question. It concerns like X-ray sources. I think you mentioned a little bit about X-ray sources, even for testing these devices. For example, soft X-rays.
Well, my favorite X-ray source has been the synchrotron light source, about which I will talk tomorrow. It's electron storage ring, and electrons radiate when you accelerate them, and when you bend them, you accelerate them, so you get light out of synchrotrons. But the traditional source is by taking an electron beam and bombarding a metal target, and that's the way Mr. Röntgen did it, and that's the way people do it in the dentist's office and everywhere else. And those X-ray sources you can buy. They are cheap. And they can be used to make soft X-rays as well. Now, there are very high-tech modern sources of even soft X-ray lasers where you fire ultra-fast visible light or infrared laser into a gas container, and you generate high harmonics, and you can generate soft X-rays that way, and people are developing that more and more.
Okay, so if there are no more questions, we thank Dr. Janos again. The UASLP chapter of the University of San Luis would like to thank Dr. Janos, and we have a small present for him.
Well, thank you. With a sombrero.
Thank you. And we, nos esperamos mañana aquí a la 1 para el juego. Los que son miembros